All right, so this is our last lecture for this entire quarter, and it's going to be a review on all the materials we went over this quarter. I also prepared like 4 sets of practice problems. So after the review, I'll ask you to vote like which kind of question you want me to go into more details, and then we'll work on it depending on how much time we have. And if I don't have time to go over it, you can see that in our annotated notes. But as a quick summary of the entire quarter, I want to go over this diagram with you to tell you like how things are connected, right? We went over 6 chapters in this entire quarter, and I want to go over with you like how exactly are these topics connected to each other. So in chapter 1, we started by talking about vocabularies in thermodynamics. So what are these vocabularies, right? What is the definition of a system versus a surrounding? Right? There are different types of system: closed system, open system, isolated system. And then comparing the system and the surrounding, they might be separated by different kind of walls. You can have rigid versus non-rigid. You can have permeable versus non-permeable, adiabatic versus non-adiabatic walls. And then we have different kind of properties, right? You have intensive properties, you have extensive properties. So these are the vocabularies that we introduced at the beginning of the quarter, and we continued using those vocabularies throughout the entire quarter. In chapter 1, we also went over calculus review, like derivation and integration. So those are the things that we want to refresh your memory on in chapter 1. We also introduced ideal gas law, PV equals nRT. The gas molecules don't interact with each other. And in chapter 1, we also went over the equation of state, right? So as a reminder, volumetric equation of state as a function of pressure and temperature, right? So the equation of state, again, it's something experimentally determined. And by say experimentally determined, we are using 2 different partial derivatives, alpha and chi, to find out what is the equation of state. Right? What is the equation of state? It tells us the relationship of our macroscopic properties, right? Pressure, volume, temperature, and number of mole, and how are they connected to each other. So that's our chapter 1. That's what we call the vocabulary or foundations of thermodynamics. And then after chapter 1, we spend time before our midterm 1 exam talking about our first and second law of thermodynamics. So moving on to our chapter 2, which is the first law of thermodynamics, it basically is a different version of saying our internal energy of the system is conserved. And what we find out that du, the infinitesimal change of my internal energy, equals to dq plus dw in a closed system at rest, no external field. And then from our internal energy, we have also defined our enthalpy. Right? So these are the 2 thermodynamic state functions that we discussed in chapter 2. And remember, H is defined as U plus PV. Right, so what is internal energy? That relates to how your atom or molecules interact with each other. It's an internal property describing that system. And enthalpy itself tells us what is the heat transfer at constant pressure. So for these kind of state functions, right, we followed the typical 3 steps. What does that mean? We start by looking at the definition of that state function. We then went over the calculation of the change of the state function. So in chapter 2, we're focusing on ideal gases. And at the end, we discuss what is the physical meaning of these thermodynamic state functions. Right, so that's in chapter 2. That's regarding first law of thermodynamics, internal energy and enthalpy. Later on, in chapter 3, we start talking about our new state function, entropy. So the same logic, right? We start by looking at how is entropy being defined. To do that, we used our second law of thermodynamics and our Carnot cycle. So what is a Carnot cycle? A Carnot cycle is a reversible cycle, consists of 2 isothermal steps and 2 adiabatic steps. And by doing all the derivation over the Carnot cycle, we find out there is a state function, which is my dq reversible over t, and the cyclic integral of this dq reversible over t always vanish, telling us the definition of our new state function, which is entropy. All right. And in our second law of thermodynamics, one of the statements of the second law of thermodynamics saying like there's no heat engine that can 100% transfer your disordered form of energy, which is heat, into ordered form of work output. And later on, we find out that using the second law of thermodynamics, we derived that eventually the delta S of my universe will always be larger than or equal to 1, where that equal sign is taken when only reversible processes taking place. All right, and then we went over calculation of entropy changes, how to calculate delta S for different processes, isothermal processes, isobaric processes, for ideal gases. And then we went over the physical meaning of entropy. Right, so we went over our derivation using the mixture of ideal gases and find out that the nature of entropy is a form of probability. Right, so entropy, the state function, describes the probability of a thermodynamic state to take place or not. Or you can write this one as K log P plus some kind of constant, where this P here is probability. All right, so that's our first midterm exam material. So the take-home message before midterm 1 is to prepare yourself with the definition of our state functions. What is heat? What is work? What is internal energy? What is entropy? Right. So before our midterm 1, we define all these terms in thermodynamics and also went over like how to calculate like delta H, delta U, and delta S. Also like heat and work of a specific process. All right, so that's before midterm 1. Now, later on, after midterm 1, we start to dive into thermodynamic relations and also trying to establish a relationship between these thermodynamic state functions into something that we actually care, which is material equilibrium or chemical equilibrium. Chemical equilibrium involves phase transfer and reaction equilibrium. We want to know how does a reaction taking place, right? So what is the criteria of equilibrium? How to use thermodynamic state functions and these calculations to predict the position of the equilibrium. So for that to happen, we went over our chapter 4. So in chapter 4, we started by defining our Gibbs free energy and the Helmholtz energy. So these are the two new state functions we defined, right? G equals to H minus Ts, A equals to U minus Ts. We went over the discussion in like what exactly are my Gibbs free energy and my Helmholtz energy. What's the physical meaning of these two new state functions? Right, the Helmholtz energy or the work function is the total maximum amount of work my system can output, where the Gibbs free energy is the maximum amount of non-PV work that my system can output to whatever surrounding we're caring about. And in chapter 4, we also went over our thermodynamic state functions. Right, so again, whenever we have new state functions, now we have like 5 different state functions listed here. So a thermodynamic relations gives us a way to generally build relationship between these state functions. So for all these 5 state functions, you want to know what are their definition. Right, so how are they defined? What kind of thermodynamic law is being used for the definition of that state function? you also want to know how to calculate the change of these state functions. Delta S, delta G, delta H, etc. Also, you want to know what is the physical meaning. Right, so obviously the definition and the physical meaning, these are the terms that's going to more happen when you have a true and false problem. And the calculation of that state function is more likely to appear in one of those comprehensive or short answer problems. Right, so let's just look at an example here. What does it mean when we say calculating the change of my state function? All right, so this one is, again, it should be a review, but we'll just do this together. Right, so you think about one of our state functions, we'll just randomly choose entropy, which is the less intuitive one for you. Right, let's say we have entropy, and since we know temperature, volume, and pressure are always like dependent to each other, right, so we just pick two of them to discuss the dependency. So here, let's see, we have entropy as a function of temperature and pressure. All right, so the goal here is how to calculate, how to express or calculate delta S for a general process between T1, P1, to T2, P2. All right, so how to approach this kind of question? Right, so in this case, what do we have? Now, if we write the total differential of my entropy, which is a function of temperature and pressure, by using calculus, we can simply write it as partial differential of ds over dt at constant p dt plus ds over dp at constant t dp. So this is just calculus, right? Simply writing out the differential of entropy. Now, what are these terms? These are the partial differential equations, right? So whenever you have these kind of partial differential equations, that tells you the relationship of your thermodynamic state functions with respect to temperature, pressure, or volume. Or if I translate this one, the partial differential of S over T at constant P, that's my temperature dependence of entropy, right? So this is something you can find in our thermodynamic relations. Now this one equals to Cp over T, and my ds over dp at constant T, this equals to my negative dv over dt at constant P equals to negative alpha b. So if you don't remember how that's being done, you want to go back and review your thermodynamic relations and try to do that again, like from the very foundation, so you know how that's being derived. But nevertheless, at the end of the day, we can express my ds as Cp over T dt minus alpha b dp. All right, so note that what we want to find out what is my delta S, or the change of entropy, considering a change of state between T1, P1 to T2, P2. Right, so in here, what are we doing? We want delta S. Now delta S just equals to the integral of my ds, right? So we just want to take the integration on both ends. And that becomes integration of ds Cp over T dt minus alpha b dp. Right, and the whole point we can do this, and this is from my P1 to T2, from P1 to P2. And the whole point we can do that is we know this is a state function, right? So it's okay if we say like T1 to T2 while keeping the pressure constant, and then while keeping the temperature constant, we're going to from P1 to P2. So we're just separating that change of state through a hypothetical isobaric temperature change followed by isothermal pressure change. And that's where these two integral comes from. Then the question becomes, how do we solve this integral, right? So there are different ways we can do it. Typically, we'll tell you what is Cp. We know that Cp is a function of temperature. Now, it might be an equation I gave you, right? Like, for example, you can say that equals to A plus Bt plus Ct squared, right? You plug it in, solve that integral calculus. For alpha V, this one is more typically, we solve for alpha using the equation of state. Now, what is alpha? Alpha is 1 over V times dV over dt at constant P, right? So if we know what is our equation of state, like say we use PV equals to nRT, you can easily solve my V equals to nRT over P, my dV over dt at constant P equals to nR over P. You plug it in to solve for what is alpha. Right? Once you express alpha as a function of pressure, we can solve this integral. Yes?
Is this only for reversible changes in entropy?
Not necessarily. Now the question is this only applicable to reversible process? So the key point here is we can build, as long as we can build a reversible path for it to happen, because my entropy is a state function, as long as my initial and final state are the same, the delta S for a reversible path and an irreversible path will be the same. All right, so that means, like, for example, if we're having an irreversible change from T1P1 to T2P2, we just have to hypothetically build a reversible path that's linking the initial and final state. All right, so this is a quick demonstration in like, what exactly do I mean by you need to know how to calculate the change of these state functions. Now this logic applies to all your state functions, delta U, delta H, delta S, delta G, and delta A. They all work similarly, right? So in chapter 4, we went over, say, the temperature dependence of internal energy at constant volume. That's just my heat capacity, right? Or my enthalpy dependence of pressure at constant temperature, right? So those are the derivation we did in chapter 4. And the whole point we did all those derivation is because it gives us a way to calculate the change of my thermodynamic state functions for any processes you want. So that's our chapter 4. And then from chapter 4, we moved on to look at chemical potential and material equilibrium. So this part is in chapter 5. Right? As a reminder, what is our chemical potential? So we define our chemical potential of substance I in phase alpha to be equal to partial differential of G in phase alpha over the Ni in phase alpha, constant T, P, N alpha J doesn't equal to I. Right, and what else do we know about chemical potential? If we take phase equilibrium as an example, basically the higher the chemical potential it is, the chemical potential differences tells you which direction your material is gonna flow. Right, so always compare your chemical potential with like temperature, right? So temperature difference tells you the direction of your heat transfer, and chemical potential, the change of chemical potential or the magnitude of chemical potential tells you the direction of material flow, right? So they work the same way. And then for material equilibrium, remember we have our 3 graphs telling you what we're expecting, right? So for entropy, over time, we see that it's always going to increase in an isolated system. And then for my Gibbs free energy, over time, we see it's going to decrease for closed system, constant Tp. And for our Helmholtz energy, we have our closed system, constant Tv. right? So whenever answering the true and false problems, and we'll see an example here, it's very nice if you just draw these pictures on your side. It's going to be very helpful to answer those questions. So for example, if I jump into some of the true and false problems. So let's just focus on these one. Like the first one, delta G is always 0 for a reversible process. Sorry. And I'm just going to highlight some of the things I think relevant. All right, so for example, my part C, D, and F, right? So in all those three questions, it'll be very helpful if we just draw it. We have G, and goes down. We see this is closed system. Constant Tp. We read the question. Delta G is always 0 for a reversible process in a closed system capable of PV work only. So delta G is 0. On which part of this diagram my delta G is 0? Right, so that's there. Right, but in this question, it's saying delta G is always 0 for reversible process at here, which is fine. But it only said a closed system capable of PV work only. It didn't specify my constant Tp, so that statement is false. All right, so you write down the figure, you find out what the question is saying, and on this diagram, you try to find, like, is it true? And it's not. It's missing a condition. Next up, the Gibbs energy of a closed system with PV work only is always minimized at equilibrium. Right, so the Gibbs energy, that's our y-axis, it is minimized at equilibrium, but again, it didn't specify constant Tp. All right, about the number F. For an irreversible isothermal isobaric process in a closed system with PV work only, delta G must be negative. Now it's talking about an irreversible process. Specified closed system, constant Tp, and for irreversible processes, where is that X? Where should I put it on this figure? It's something here, right? So if I take any point at my 1 and 2, and you compare the delta G, that delta G is always going to be negative. So this one is true. Right, so this is a demonstration in, like, whenever we're working on these kind of true and false problems, if you're less familiar with that statement, just draw that picture and it's going to help you in getting to the answer, like, quickly. All right, so let's go back to our diagram here. And now we're talking about Chapter 5, right? So we went over chemical potential, material equilibrium. We also discussed my standard thermodynamic formation of reactions. So in this whole part here, we're talking about the appendix table, right? Or the standard state thermodynamic table. So I have a small version in here. So ask yourself, for everything in the table, do I know what that means? So when I say my delta H naught 298, the standard enthalpy of formation, right, where it comes from, how do scientists measure it and calculate it? And how to use the thermodynamic table to find out the reaction, the enthalpy of the reaction, the conventional molar entropy of the reaction, and the Gibbs free energy of the reaction. In here, we also have the Cp naught term, which tells you, like, how to use that term to help you find out the temperature dependence of enthalpy. Right, so for the thermodynamic table, know where they come from, know how to use it. And then at our last chapter, which is chapter 6, we started our discussion of reaction equilibrium. Right, so in this part, we have two fundamental equations, like delta G naught equals a negative RT ln Kp naught. And my d ln Kp naught over dt equals to delta H naught of RT squared. All right, so the first one links gives free energy of the reaction with equilibrium constant, where the equilibrium constant is defined related to the equilibrium composition. And then the equilibrium constant itself is dependent on temperature, and that's our Van 't Hoff equation. All right, so for chapter 6, it's more application. So as you can see, our entire quarter is we started somewhere abstract, right? We started from abstract derivation and definition of thermodynamic state functions. And later on, we start to apply those thermodynamic state functions into things that we care about as chemists. What is reaction equilibrium? How to predict the shift of reaction equilibrium, etc. But knowing the definition, knowing these foundations and derivations and their relationships, they're important, because otherwise you won't know like where they come from, right? Why do we care about entropy when we're talking about reaction mixture? All right, so that's a quick summary in our entire quarter. I have posted a much nicer version on our annotated notes. And now we have about 25 minutes left. So I prepared 4 different questions. I'll ask you to vote. The first one is our ideal gas reaction shift, like how does changing of state shift your ideal gas reaction mixture, etc. And then we have a derivation example in like how to derive like your volume dependence of internal energy with a equation of state. And we have a calculation example. So this one is more like related to our chapter 6, right? So when temperature is changing, how do we calculate your equilibrium constant at different temperature? And at the end, we have our conceptual example, which is true and false problems that we did. So raise your hand. Okay, so just raise like 1, 2, 3, 4, and tell me which one you want me to go over. Okay, I'll do 1 and 3. I think that's the most voted. Okay, number 1, ideal gas reaction mixtures. So for this one, it's basically thinking about how is my equilibrium quotient change compare with respect to my equilibrium constant. So let me write down what do we know about the equilibrium constant and the reaction quotient, and then we'll start doing that from there. So what do we know? We have our equilibrium constant, right? So Kp naught, we define that to be the product of my partial pressure at equilibrium over standard pressure to the stoichiometric coefficient. And my reaction quotient is defined as my partial pressure to the stoichiometric coefficient. So when looking at these two, the first thing here is my equilibrium constant is only a function of temperature. And that relationship is given by our Van 't Hoff equation. Right, so that's how our equilibrium constant is going to change. It's only a function of temperature. What about my reaction quotient? For my reaction quotient, we have 2 different scenarios. One, at constant volume, right? So if my total volume is constant, then my partial pressure equals to my nRT over V. So my total volume is not changing. It's ideal gas mixture. So for every component, my partial pressure equals to nRT over V. Or if we're talking about constant pressure, then my partial pressure equals to my mole fraction times the total pressure P. All right. And let's see, how do we use these information to quickly solve the question of predicting the shift of equilibrium constant? And first thing first, first question, we're asking for temperature is decreased at constant pressure. So that means I just write it as isobaric temperature decrease. So it's isobaric, my pressure is not changing. We're not adding any reactant or product into our mixture, so my Chi is not changing. So we can write down this to be my QP not changing. All right, but temperature is decreasing. So my equilibrium constant is changing. So I'm focusing on how does my equilibrium constant change, right? So originally it was at equilibrium. So in my initial state, my QP and my KP is equal at equilibrium before the temperature change. And now the temperature start to change. So we have d ln KP naught over dt equals to delta H naught over RT square. Right, so what is my delta H naught? Right, so we have our reaction. That's the delta H naught of the reaction. PCl5 goes to PCl3 plus Cl2. So we can use the appendix table. Right, so my delta H naught of the reaction equals to the stoichiometric coefficient times the standard enthalpy of formation. You can do that yourself, but I did the calculation that equals to 87.9 kilojoule per mole. Or this is an endothermic reaction. For endothermic reaction, delta H is positive, so my temperature drops, my equilibrium constant also decrease. All right, so my QP is not changing, my equilibrium constant drops, my QP now is larger than my equilibrium constant, so the reaction is shift backwards. And let me write that down as well. So whenever we have my QP naught to be larger than my KP, and my QP naught is smaller than KP naught, we're predicting a forward reaction. Yes.
I just want to make sure I have the reasoning correct. If it was negative 87.9, you would say that QP is increasing because it's getting, like, as temperature increases?
Right, it's going to be more easy if you just plot my temperature. And here, imagine we have some kind of delta H that's negative, right? So what is my K ln P? So we know that my D ln KP over dt is delta H naught over RT square, right? So the differential or the slope of my ln KP versus temperature, it's dependent on the sign of my delta H naught. Now this one is like basically what we're expecting. It's different dimensionality, but we're expecting my KP naught to drop with respect to temperature if delta H is negative. Right. Alternatively, if we have like positive delta H naught, so we're expecting this one to be increasing with temperature. All right. So it's again, it's just mass. All right. That's our first question. Second question, we have our isothermal volume decrease. Again, if we read it together, it says volume is decreased at constant temperature. So I just translate that into isothermal volume decrease. So isothermal volume decrease instantaneously you can write down for isothermal as my Kp not changing. So my equilibrium constant is not changing. Right, so my volume is changing. And what do we have? What else do we have here? We want to use this relationship here. So we have our Pi equals to Ni over RT over V, and all my partial pressure would increase with my volume decrease. My volume is decreasing, right? So all my partial pressure will increase. Right, so Ni is not changing, R is not changing, T is not changing, volume is the only thing that's changing. So all my partial pressure will increase. And we have my Qp equals to the product of my Pi mu I. And in this reaction, what do we have? We have the partial pressure of my product, PCl3 to 1, partial pressure of my Cl2 to the power of 1, and the partial pressure of my PCl5 to the power of negative 1. So when all my partial pressure are decreasing to the same dimensionality, what we care about is how many, what's the stoichiometric coefficient here? All right, so we have 2 gas in the product, 1 in the reactant. So when all my partial pressure are decreasing, we're saying my product gas, this one on the top, is decreasing. And what does that mean? So let's say this one, these 2 are decreasing, and this one is on the bottom, and that's gonna increase. So we're decreasing more comparing to what we had. And my Qp will be smaller than my Kp. I might have to double check if my answer key is correct for this one. Wait, yes, sorry. That's why I was like, why am I, that's my bad. Okay, so yes, you're right. So my partial pressure are increasing, so we're increasing more in my product because my product has more gas, and this one is decreasing less. And then my Qp is larger than my Kp naught, and that is a, again, backward reaction. These are the questions that's very easy to get wrong, so make sure you're writing down every step along the way. All right, next up, we have some PCl5, which is my reactant, is removed at constant temperature and volume. So again, constant temperature, my equilibrium constant is not changing, and we have Pi equals to Ni RT over V. Right, so my PCl5 is removed. So the partial pressure of my PCl5 is decreasing since the number of mole is decreasing of my PCl5. And you look at my reaction quotient. My PCl5 is my reactant. So my PCl3 times PCl2, so on the top, these are not changing. And on the bottom, my PCl5 is decreasing. So my reaction quotient is increasing, and that thus predicting a backward reaction. Right, and then the 2 questions are related to each other. So part D, we're adding an inert gas, helium, into the reaction mixture at constant temperature and volume. Part E, we have addition of helium gas at constant temperature and pressure. So in both cases, since we're at constant temperature, my Kp naught is not changing. But for my question D, since my volume is also kept constant, so my Pi equals to Ni RT over V, also not changing. Right, so the number of mole of my reactant or product gas is not changing. Total volume is not changing. The partial pressure of the species is not changing. So for part D, we're predicting the equilibrium to be not shifting. All right. And what about part E? So for part E, again, constant T, we say that my Kp naught not changing. And my Pi then depends, right? So my Pi, again, you can write it as Ni RT over V. But in this case, when we're adding the helium into my reaction mixture while changing the volume, wait, actually, let me change this. So Pi equals to chi I times P. Let me keep myself consistent. So the total pressure is not changing, but addition of the helium gas will change the mole fraction of my reactant gas. So the mole fraction of all my reactant and product will all decrease. All right, or we'll say all Pi will decrease with the addition of my inert gas, helium. And then it becomes the same question, right? So we have our Q equals to the product of my Pi to the stoichiometric coefficient. So have two gas in the product, one gas in the reactant. So when both of them are, when all partial pressure are decreasing, my reaction quotient is also gonna decrease. Right, so I put these two next to each other just to make sure when answer these questions, read the question carefully and know, like, is it constant volume or constant pressure? Because it might be very different. All right. Okay. One more question, practice question together. I'll skip the derivation problems and you can check your answer with the answer key. And let's look at the calculation example here. So we read the question together. It says for a certain ideal gas reaction, we have Kp naught given at 298 Kelvin and 315 Kelvin. We ask you to find the delta H naught and delta S naught of the reaction. Also state any approximation you are making. So for this kind of question, the first thing you want to ask yourself is how big is my delta T, right? So one of the key approximation we discussed is whenever my delta T is small, which in this case, my delta T is only 17 Kelvin. We can assume my delta H naught is not changing. Or my delta H naught is constant. And what else do we know? So the question asks us to find delta H naught, delta S naught. So we have several pieces of key information we need, right? So we have delta G naught equals to negative RT ln Kp naught. That's one thing we know. Second thing we know, we have our Van 't Hoff's equation, right? D ln Kp naught over dt equals to delta H naught over RT squared. Or if we use this assumption here, we can simplify this by taking the integral on both ends to have ln Kp naught at 315 minus ln Kp naught at 298. That equals to delta H naught over R, 1 over T1 over 1 over T2. Well, this yellow equation just comes from solving this integration equation. And then how do we solve this problem, right? So the first thing first, it's asking for delta H naught at 298 Kelvin and delta S naught at 298 Kelvin. So we do not have a way to solve for delta S naught, but what we do have is delta G naught at 298 Kelvin must equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. Right, so what are the things we know? So this one, delta G naught at 298 Kelvin, we can directly solve it using delta G naught 298 Kelvin equals to negative RT ln KP at 298 Kelvin. R is a constant, T is 298 Kelvin, we know it. And this one is the Kp naught at 298 Kelvin is 0.84. That's something we get, right? So simply plugging numbers, we can solve for delta G naught at 298 Kelvin to be 432 joule per mole. Simple plugging number, that's our first step. And the logic behind knowing how to set up this calculation is here, right? We don't have any way to solve for delta S. We must start solving my delta G first. And what about my delta H naught? Because that's something we need to solve for my delta S, right? We have our Van 't Hoff's equation. So that's my line Kp naught at 315 minus line Kp naught at 298 equals to delta H naught over R over 1 over T1 minus 1 over T2. So what are these numbers? This one is the Kp naught at 315, so that's my line 0.125 minus line 0.84 equals to some delta H over my gas constant 1 over T1, T1 is 298 minus 315, and you can solve for delta H from here. And we can solve for delta H naught equals to negative 87.5 kilojoule per mole. Right, and then it's just plugging numbers into this equation. So the hardest part of this question is where this approximation comes from, right? And it also gives you the hint and to ask you to state any approximation that's being made. So this is the hardest part of this question. That's assuming my delta H is constant. And for logic behind this kind of question, I still, again, like the best way to approach a question, especially when you don't know where it's coming from, just write down anything you think that's relevant to the question that's asking. Right, so this one is asking us to calculate my delta H and delta S with an equilibrium constant. So we're talking about how is my thermodynamic state function related to equilibrium constant. So it wouldn't hurt to write down delta G equals to negative RT ln K. You're effectively, you will be needed eventually. Also, we have equilibrium constant at different temperature. So again, write down the Van 't Hoff equation and start thinking about it, right? So now we have the Van 't Hoff equation. How can I solve this Van 't Hoff equation? And then it becomes obvious. Okay, so I need to know how does my delta H naught change with respect to temperature? And then you can say, okay, my delta T is small, so we can assume delta H is not changing, and then you have everything you need to solve for this problem. All right, so that's the logic behind my mind when I see this kind of question. So it's not like, okay, started by, I know which equation, like just grab an equation and start plugging in. It's really hard to do it that way. It's more likely to write down what are the things we know, and then go back to see like, okay, so these are the things I need. Do I have them in the question? Or is it safe to make that assumption? All right, that's everything from me. I left a derivation problem in here and also a true and false problem. We went over 3 of them to show like how they're related, but feel free to practice on them. And again, as a reminder, I have extra office hour this afternoon between 1 to 3. So please stop by if you have any questions you want me to answer. And reminder for some end of quarter surveys, course evaluations, extra credit opportunities that's due tonight. Your worksheet is also due tonight, so don't miss those deadlines. And I guess good luck studying, and maybe I'll see you in the afternoon or I'll see you in the final. Bye-bye.